Hello everybody. This is the sixth part of our course with image processing with MATLAB. Today you will have frequency domain filters. In the previous part we used spatial domain filters. If you didn't see it, please watch that before, and you will get some information about how to make a kernel and how to apply your filter on the image. And here we want to have a look at the frequency domain filters and how to use some filters that you saw in the spatial domain, how to use them in frequency domain, and also some other filters that you can use in frequency domain. All right, so we can just take a look at the process first, and just quickly we will go to MATLAB. So I come here and I bring a white slide. Just if you imagine that this is the spatial domain, okay, and this is frequency domain. All right, so I can write here, in fact, just to be much more clear, I can write spatial domain and this square is for frequency domain. All right, so we have an image that it is already in the spatial domain. All right, so we can call it input image. Okay, input image. All right, you have the input image, and we can name it, for example, f, x, and y. All right, so next is to apply FFT transformation on this image that is in a spatial domain to bring it to frequency domain. So I here just I write FFT, or I can write Fourier transform okay. All right, and then the result will be the output of this part, that will be F, U, and V. Okay, so that is an image in the frequency domain. Okay, so you see that in frequency, in spatial domain, I write them with small letters, and in frequency domain I use big letters, all right, capital letters. So now that you have your image in frequency domain, we need to apply our filter. All right, so we apply a filter in frequency domain, and for example I write apply filter. The filter, for example, we can use H for the kernel, so I say H, U, and V. All right, and here you will have another image that we call it, for example, G, U, and V. Okay, that is an image in frequency domain. Again, I write it with capital letter. All right. So now we need to bring it back to a spatial domain to visualize it as we like and to understand it. So we will apply the inverse of Fourier transform. So I say inverse FFT. Okay, fast Fourier transform. Here just I wrote Fourier transform. However, we will see it again in MATLAB. So after this transformation, the resulting image will be the output image that is again with a small g, g, x, and y. All right. So you see that how we go from spatial domain to frequency domain, apply our filter, and we come back to the spatial domain and we show our image. All right. So this was the process that we are going to do and apply it on images. In this case, we can go to MATLAB and see here. So just before start, in fact, I prefer to just show you the function in the documentation of MATLAB. So here we are, FFT, fast Fourier transform, and you can apply it on just you see x, okay, that can be an array, okay, and the result is y, all right, that is in frequency domain. And you have other options and you have examples for it, so that you can use and be fluent in using this function. All right, let's start with an example. So I just open and edit. We just can read an image. Imread. So for example, I just bring again the image of the city. Okay, then you need to apply the FFT. Okay, in fact here I should write FFT2 because we want to apply it on a 2D array that is an image. So you see that this was FFT that I showed you, but for images I use FFT2. Okay, and here it is, and you can see that here you have example with images. All right, so this also something that I forgot. All right, so FFT2 of I. Okay, so now F is our image in frequency domain. All right, but however this image is in frequency domain, so it has a real part and an imaginary part. In this case, I say real equal to function real extracts the real part of the image for us, so real f. All right, and just I can show it also, im show real, and then we can extract the imaginary part, so I call it image, and just with the function image you can extract it, image f. Okay, so again, we can show it. So I make another figure and show image. All right. So now let's see the results. Okay, so just I name it as a test one. Okay, I had it before, so I think something like test 20 will be okay. All right, so we will have two images like this. All right, so the first one was the real part of the image, and the second one is the imaginary part. So here you see that we cannot understand anything. All right, and the visualizing of this result is not good for understanding of human. So let's just a little change something. For example, here we can calculate the absolute of f, okay, and show it. So for example, I say a equal to absolute of f, and show a. All right, so just I can comment this part and I show it. So you see that it is complete white. So still it's not good. So what if I take the logarithm of a, all right, but I add 1 also to it, so, and now I run it. So still nothing. You know why? Because we have some values that are not covering all the range, and just you can use two brackets here. This helps to show the results. In fact, here I needed to change the image to a gray image, and so it will be visualized. All right, so this is the result. All right, here you see that our image on the corners is brighter, and in the middle is darker. So we need just a little shift to apply in the phase. Okay, and with the phase shift, so the center frequency will be the center of the image, and the visualization will be much better. In this case, we can just calculate fs. For example, after a, just I write f shifted equal to absolute of fft shift, okay, f, and we come and visualize this now, and you see that this is the result. So you have the image in the center, you have the brightest values and frequencies, and the edges the darkest, and this is showing that in the center of the image, in the center of this image, that is the our image in frequency domain, you have the highest frequencies, and as much as you go farther from the center, you have the lower frequencies. All right, so now we are ready to apply our filters on this image that is in the frequency domain. I prefer to open another edit, and I will start with just CLC, clear, and close all. Okay, as always, we start with these functions. You may know them. To CLC clears the command window for us here. If I apply CLC, you'll see that it will be cleaned. Clear clears all the variables that are in workspace, and closes the windows and figures that are open. All right. So here I can in fact copy these. All right. So we read our image, we change it to gray. In fact, it is better to make it double. Also, I say im2 double I. This really helps you in the processes and not to have a problem, and normally the results will be better and you won't receive errors. So let's do that. After that is bringing our image to frequency domain, and now you can make your kernel. So I write, for example, h equal to f special, for example, average filter that we use. So we make this kernel, and you write h equal to what? Now we have a kernel. It is also in a spatial domain, and we need to bring it to frequency domain. So here again we apply FFT2, but you know that this just a 3x3 window, so we need to extend it to the size of our image. So in this case you need to say h and size, f and 1 and size f and 2. Okay, this will be extended. In fact, it is better that I write capital F, that is our image, in the frequency domain. And after this we need to just multiply our kernel to the image. So we will say h multiplied by f. In fact, here we say dot star, that is element by element, and we have now a kernel that is at the size of our image and the image. So we multiply them pixel by pixel, and we are traveling to a spatial domain again. So the inverse of FFT2 is applied on G. Okay, that's it. I think now we are ready to to show the results. I hope that I didn't do a mistake. So im show f, the original image that was in a spatial domain, and to G after applying averaging filter, and again is an image that is in spatial domain. So I just say test average field. Okay, and I show it. So I think I have done a mistake. 1 to 1 f. It is not if, it is I. And so the result that is G. So I need to check here. This is G, this is F. Have I, so if, yes, now it is working. And if you look at the result, you see that uh, it has worked completely similar to what we did in the spatial domain. And the averaging filter, that is a smoothing filter, has been applied on the image, and this one is smoother and less sharp than the original image, and it has been done. Here I will introduce you also the function of freak z2 that just is so similar to ft2, and it does also the extension of the kernel for us. So you could just here instead of these, okay, use freak z2, okay, frequency z2, age and size of f and 1, size of f and 2, and we also apply just an IFFT2, IFFT shift of H, also for shifting the phase that is needed for this function, and it will be okay, and you can apply it. So I made a mistake, so R was missing, so you apply it. So just here, because we have a phase change, it works like this. We need to change the sizes like this for compatibility of this function, so it will be okay. And just you need to change this, okay, and first put the dimension of kind of, you know, x and then y, all right, and but it works perfectly. And this function also you can use, and also check it please on the documentation. So you see that here now, by this technique also, you can apply all those filters that you saw on the previous part of this course. In a spatial domain, we applied them. They were for smoothing, for finding edges, for sharpening the image, for removing noise, etc. So just by this technique, you can do those and apply them. And I propose you to do this. And if you had a comment, if you had an interesting result, you can share it with us in the comments. So, however, in frequency domain, you have the ability to use other filters also. In the time that you feel that you have a noise, that this noise has a special frequency, and this noise has been repeated during your image with a frequency, all right? And you think that the spatial domain filters do not really help, and you need a frequency domain filter. Okay, in this case, the elision and removing this noise will be much easier for you to remove it in frequency domain, because you just need to recognize that frequency and then remove it. In a lot of cases, you have a high frequency or a low frequency noise uh, in, in the images that are taken by a camera in a spatial condition in a factory, that there's this noise almost always there. So by just the frequency domain filter, you can remove it. So how we apply frequency domain filters? Before, we just want to know a function in MATLAB, and after that we will go to those filters. The function that I'm going to introduce you is mesh grid. Okay, like this. What does it do, mesh grid? You just need to imagine that, for example, we have one array like A, okay, 1, 2, 3, okay, and you have B that is like, for example, 10, 20, 30, all right? If you want to have a summation of these two matrices, element by element, normally you need a for loop, okay? But meshgrid does this work for us much faster than a loop, and much stronger. So you just need to write mesh grid, okay, A and B, and I write here the outputs UV, okay, execute. You see, it gives you two matrices, okay, that if you add them together, you will have all the possibilities, okay, 1 with 10, 11, okay, 1 with 20, with 30, and on the other side, 2 with 10, 3 with 10, 2 with 20, 3 with 20, etc. So now it is pretty easy to add them, okay, by addition of U and V. All right, so now we want to make the filters, all right? In this case, if you remember, or let me show you in this image, you see that this image is not in a spatial domain, that we needed to treat it from the first line by line to the end. Here we have frequencies, and you see that they are from center to the edges. In this case, for keeping some special frequencies or removing some special frequencies, we need to travel from the center toward the edges and remove part of the frequencies. And you know that the highest frequencies that represent the details and more information and are valuable are in the center. So we need to here we need to now if I copy this, okay, copy figure, I'm sorry. So if I come here and show you on this image, so we say that now for treating in frequency domain, we need a circle around, okay, to remove the frequencies inside of it or outside of it. Okay, so in this case, we need a to build this circle and apply it on our image. How to make it? We need to make a distance so function, okay, a d function, and by applying it you will have your image filtered, and then we bring the result to spatial domain to restore our image. Okay, so I come to another slide to introduce the first filter that we are going to apply. Let's start with low pass ideal filter. Okay, so low, oh, I'm sorry, the W is a low pass ideal filter. So how is it? H I for ideal of U and V is equal to 1 and 0. Okay, for this filter, that is it, it is ideal. Okay, because ideal filter, you see, from a distance completely removes the frequencies, so it is ideal. It is one if it is low pass, so the lower frequencies should pass. In this case, we say if D, U, and V is smaller or equal to D0, and if D, U, and V is bigger than D0, bring it to 0. Okay, those frequencies. So you see that this filter works like this. Okay, 0 or 1. Okay, this is our filter that we are going to apply. And the second one that today we are going to see is Gaussian filter. Okay, so we again start with low pass. Filter, and the formulation that we need to apply, in fact I could write it with the same style, so I can write Hg of U and V is equal to e to the power of this minus parentheses D U and V, this to the power of 2, okay, and on to sigma to the power of 2, okay. And you know that this sigma controls the shape of your Gaussian filter, okay. Okay, how much it is thinner or wider. All right, I really invite you to take a look at the definitions and shapes and details of these techniques on the internet or other videos that you can find elsewhere, and it will be really helpful for you to understand them and apply them on the right time. And next one, let's see the Butterworth low pass filter, and the formulation that is HB of U and V equal to 1 on 1 plus D U and V on D0, okay, bracket is closed, to the power of 2p. All right, and the shape of this low pass filter, so it's like this. I can do this also, and okay, something like this. Not very precisely, but I hope that it is helpful for you. Now we have three more applicable and famous low-pass filters that we can apply them, and after that we can take a look at the high-pass filters. All right, so I change this is N, not P, in fact. So N. All right. So before start, we can first create the distance function that we talked about it, to make the circle and to remove or keep inside of that circle. All right, so here I make a function for it, and I call it function dismat. Okay, for example, distance matrix. All right, something like this. In MATLAB, if you want to make a function, just you write function word, and you see that the color turned blue. Okay, and then you write the outputs. Okay, so the output, I say U and V. Okay, U and V capital, and then equal to the name of the function. Okay, and the inputs that I will have, for example, M and N. Okay, so anywhere else you can call this function, okay, with two inputs, and it will give you two outputs. So, and the names are not important. You can call it anywhere else by other names. Okay, it is okay, but this is the format of your function. All right, you can close the function also with end here. So and then write inside of the function. Normally at the beginning of your function, it is better that to add a description of your function, what it does. So you can just add something like this function computes a distance matrix for frequency domain filters. All right, and here normally you can introduce the inputs that now I don't do it, but you do it to have codes that are clear and understandable for others. All right, so what we should do, uh, I create positive integers and then I make it mirrored from the center, all right? And just we need to use mesh grade to make a complete circle, okay? So now you will understand. For example, I will say u equal to single of what? Of 0 until I can write it like this, m minus 1, sorry, okay, it's okay, and I close it. If you want to see the results, I will show you. For example, you can check it here. If we have, for example, m10, okay, so single gives you from 0 to 9, 10 minus 1, just integers with the same distance, and so then we can treat it later and you will see the result of the other one also. So let me define v also, and I will show you v single of 0 to n minus 1, okay, so it will be the same result. And I say IDX, okay, for indices, find u bigger, oh sorry, so bigger than, we want half of the numbers, so I say m on 2 and close it. So find is a function that gives you the indices, gives you the places of the integers, okay? So for example, we had, I can show you also the result of this step also. So here, this result 0 to 9 is saved in n's, okay? So I say n's, that is answer, m was 10, okay, and you see the results, okay? It gives you the indices. It says that the elements that are bigger than 5 are in element 7, 8, 9, and 10 of this matrix that is n's, okay? So, and here you will see that if we have u of idx, okay, u of these elements that were 7, 8, 9, 10, those, find them, take them, and subtract them from m to produce negative values. All right, so I just need to repeat this also for v id y in y direction, y v bigger than n, and v id y, sorry, v id y minus n, okay? And here just we need to apply mesh grade and everything is okay. U and v equal to mesh grade u, and it's better, in fact we need to change this, okay, v and u, and the result will be the correct size. So Now this function is ready, and if you just save it, you'll see that MATLAB itself saves it with the function name, because if you change the name, MATLAB won't recognize it. So just keep the name like this and save it. So it is already saved in my directory, and I will go to another edit for creation of the filter. All right. Let's come here and start our first filter. So I start with CLC, clear, close all, and just I can add some sections, to make just by double percent sign, you can add a section. You see that it made the blue line here for us to be for the code to be readable and easier to read. So here I say ideal filter, okay, and here I say image, read image, okay, read image. So for read image, it's better that I use F, because in the first slide I said that let's use small letters for spatial domain. So let's read it. Imread, for example, animal.jpg, okay, and then you have F that needs to go to gray level. F, just I use F again, and I told you that it is much better to change it to double, so it will be really good. And now we can add a section for add noise, to add a little noise to image and compare it with the original image, so it will be nice. So I say F equal to noise, if, and for example Gaussian, and Gaussian has a parameter, so I add 1,000. Okay, so F is noisy, and now we can go to frequency domain. So I will say F capital is equal to F52 of F. So this is F that now is in frequency domain. What else we need? We need a D0. That's just I just determine it as 50, and we want to say that for the distances less than D0. So in this case we need D0. So you define it as what you like, and also you can change it later. And here I say U and V now equal to this mat, okay, distance matrix, and you needed to give M and N. Here MATLAB also shows you, and M is in blue, it says that input M. So for M I say size of F and 1, and for N I say size of F and 2, and close. So here now we can make the filter, make filter. So for our filter I make a zeros matrix. Okay, size of f and 1 and size of f and 2. Okay, and I say ind for indices equal to d smaller or equal to d0. Okay, in fact here we need to use we need to create d, okay, the distance matrix that I forgot. Here we have the output is two matrices that is the output of the mesh grid, and the distance matrix we make it with hypat, okay, function that creates the distance matrix for you. So u and v. So we also have d here. So now that we have the distance, we have a circle, okay. Now we create another matrix that is our filter, that is our mask, that we want to apply this distance using that on our image. So what to do? We create a matrix of zeros, and we say that for this region, okay, that is the d's are smaller than d0, make it white, okay, make them all 1 1 1. Okay, so when you apply it, when you multiply it on your image, the parts that are 0 will be applied to the pixels, and so they make them 0, and the pixels that are 1 will have the same value. Okay, so those frequencies are kept. In this case, you need to say h simply of these indexes, okay, equal to 1. Okay, so now let's multiply it. Apply filter. Okay, so I say g equal to this h multiplied by f, pixel by pixel, and bring it back to spatial domain. All right, so now I can add a section for show results. So I can say subplot 2 to 1 im show. For the first part we can show just f. Let me just copy this, paste. Okay, because we have 4, 2, 3 and 4. So here f show g, show big F, show big G. Okay, and let's apply. We need to save it. We say ideal field. Okay, apply. I received an error into gray. So we need to just check your RGB. I think it was just RGB to gray. I can check if F is just gray itself. So I make a comment and execute. I have another error, G. G is not recognized. I made mistake here. This is big G, so it is like this. I didn't, in fact, uh, it could be better that I show the results with shifting them, and yes, in fact, here we cannot show the frequency domain images in this form, so let's just as before, okay, write it with logarithm. So we can write logarithm of absolute of FFT shift of F, okay. Here also I can put 1 for the positive values, and like this. So you see that it is working well. So in this case, we can just copy this here also and put it here. So instead of F, we use G. Okay, to see it like this. Yeah, it is interesting. And you see that ideal filter. So just sharply cuts, you know, part of the frequencies, okay, and on the edge is not smoothly removing some frequencies, and just sharply is cutting some frequencies from here. 1 unit inside is kept, 1 unit outside is removed, okay, and cleanly it has removed the frequencies. Also, you see that the resulting image is good, is not bad. However, you see that it is less sharp, okay. It is maybe less noisy, but it is less sharp, okay. So this is the functionality of ideal filter, all right, that you can try it and um, change the diameter of the circle and see the result. And also you can try it on different kinds of noises and see the results. Okay, let's so go to another filter, so I can just copy and paste the code to a new file. So until im noise, everything is okay. And you come to frequency domain, we bring it to frequency domain, okay. And you can take a look at the formula, okay. Here you don't have D0, and just we remove D0 here. Then you have sigma, so here I introduce sigma. I just start with 30, okay. And then we use this mat, and then we use hypat. So, and we come to make filter. We don't need here matrix of zeros, because we are just going to make our filter with the formula that is applied. on uh, on the image. So I write exp of, I make parentheses, minus d to the power, sorry, of 2, and then on 2 multiplied by sigma you should care about the small and capital letters because MATLAB is sensitive to them, and this to the power of 2. Okay, if you see the formula, it was like this, and I close this. So this is H that is going to be our filter. Just I have the space here, I remove it for clarity of the code. After that, we need to apply our filter, and we need to bring it back and show results, and it looks to be okay. So I say Gauss field. I saved it and I run it. So this is the result, and you see that it's been pretty strong. Maybe I can just reduce the sigma and see the results, or maybe 3. So it is still strong. So if I say 0, 5, what will be the result? So yes, you see that it is becoming more clear. Even less is okay. All right, so the result is not much clear. However, you see the changes that so the noise has been removed partly. However, the image also is less clear and a little blurred. Okay, so if I make it a bit more strong, so you see that it's been really working well in cleaning the noise. Okay, if you look at this area, or if you look at this area, you see that the Gaussian noise has been removed very well. And here, if you look at the result in frequency domain, you see that now on the edges of the distance matrix that we applied, it has worked smoothly, and smoothly has removed some frequencies. So don't forget to practice more on this filter also, and the next one. So let me copy our code and just come to the next one. So we come here in noise, F52, we don't have sigma, we don't need sigma. I remove that, and this math and high path you need it for make filter, so we need to change it because our filter is different. So we say 1 dot slash, it's better to put parentheses, 1 plus d dot slash d0 to the power of, let's use parentheses, 2 multiplied by n. Okay, and if I need to close parentheses or not, it's okay. Now it looks okay. Yes, 1 plus this part. I also can put it in parentheses. Here also it is ready. So we need a d0 that is equal to 5. We have n, it's okay, and that's, I put it's just equal to 1 for now, and these two should be defined before h. If not, you will receive an error. And then apply the filter, and then bring it back to spatial domain and the results. So I say but field, and this is the result. Okay, so you have seen that in fact it has removed the noise also. It is really interesting, but you see that um, we have lost some of really bright pixels, but still the quality of the image is good. And in the frequency domain, you see that how it has treated the image, and you see that it has been very smoothly removing some pixels, removing some frequencies, and the rest that are there, and just you need to play with the parameters and make the filter stronger or weaker. So now you can apply high pass filters, okay, high pass, ideal, Gaussian, or Butterworth. For this, just simply we need to calculate the complement of your filter. So in this case, just simply you can just calculate it with 1 minus h, h equal to 1 minus h, and by adding this to your code, you can reverse your filter, and instead of letting low frequencies to pass, let the high frequencies to pass, and so you will see the result, and you will see that you will lose the details and sharp parts, and by omitting the most important information of the images. So you can see that how you can use those filters for some cases and for some noisy images. I don't do this part as a practice for you. I hope that you enjoyed it, and thank you very much for watching. Thank you for liking the video, for subscribing, and for proposing it to your friends, your colleagues. See you soon. Thank you very much.